I would say it's about time to get started. So thanks for being here and welcome to our webinar on gVisor, Kata Container, Firecracker, Docker. So basically who is who in the container space. And maybe just a background story why I decided to give that talk. So being at the last KubeCons and overall being present in this container ecosystem, I basically felt it was getting harder and harder. There were more and more logos. And so this is kind of like the TLDR for our talk. We just want to kind of divide those logos and give some kind of overview for people to understand, first of all, why are there so many new projects? And what does it actually mean for us using containers, using Kubernetes? So how do those projects relate to each other? And what I actually should be aware of and what I can also maybe just ignore for now. I'm Jörg. I'm the head of engineering at machine learning here at Arango DB. Prior to that, I actually built a lot of container infrastructure in healthcare space, at Mesosphere, or now D2IQ, where I actually worked on Kubernetes pre 1.0. So seen quite a bit of change in this container ecosystem. And I always found it super fascinating what it actually means, and also what containers actually mean, and what they enable us to do. But you might actually wonder, Arango DB, for those of you who don't know, it's a multi-model database. So basically we can handle graphs, we can handle documents, and we can handle key values in like the same native storage engine, and you don't have to switch between different databases. It's an open source project, so you can also contribute. It's distributed. Graphs can span multiple nodes. We have AQL, which is like a SQL-like multi-model language, so basically supporting all those different models mentioned above. And we also have, to a certain degree, asset transaction in Arango DB. So, as mentioned, you might wonder, why do we, or in this case, I care so much about containers? And if we actually look what's happening, so containers are becoming more prevalent in the database ecosystem as well. So for example, if we just take a look at the CNCF, so that's the Cloud Native Foundation landscape, we see there are actually like a lot of projects, including Arango DB, listed at like under databases. Also, if we see what customers and users are using to deploy Arango DB, we see more and more container-based deployments. So first of all, there's our official Docker image. Then there's our Kubernetes operator, which is being used by many people to set up a full-fledged and operate a full-fledged Arango DB cluster. And at last, there's also Arango DB Oasis, which is our managed service for Arango DB. So as mentioned, Oasis is actually, it's running on Kubernetes. So we ourselves, we leverage managed Kubernetes services to deploy it. So you can already see we deeply care about those container technologies, and we actually have to understand what is the implications of those different container projects. First of all, for our users, deploying it themselves, deploying it on Kubernetes, and then also for us internally, for example, building Arango DB Oasis. So if we take that initial image with all those different logos, I think the first attempt to kind of divide that, and this is also kind of the structure for our upcoming webinar here, we can kind of structure that in container runtimes, so kind of tasks with just running and starting containers, managing and monitoring containers, and then on the other side, kind of more secure containers. So the question is, how can we kind of bridge this gap between containers on the one hand and virtual machines on the other, where also a number of projects have came up. So I think this is a reasonable way. Not all projects fit nicely into one or the other, some are like in between. But I think this is a good shot for us to kind of divide that space, and we'll see how that works out. But before, let's actually talk about containers a bit. So for me, always kind of this most important lesson is there are actually no containers. There isn't a defined concept of what is a container. It's just a mix of actually different tools. So for example, if I just run like a Docker container, so here I can Docker exec, and there I have my Nginx running in there. But if I actually look at that from the same machine having root access, I can actually see it's running on that machine. So being an admin on the same machine, I can actually see the same Nginx process just with a different process ID. So there we can already see it's quite different compared to virtual machines. It's basically just a different running processes, which are more or less isolated from each other. So they have isolated views. So for example, here we see PIDs here at the beginning. So the process IDs, you can see like internally inside the container. So in our Docker exec, we get a different process ID compared to what we see like on our host or root view kernel. And this is what we just keep in mind, especially in the second part of this talk when we talk about security, that basically normal containers, normal Docker images, they are just different process groups running on the same kernel, operating system kernel. Whereas if we talk about virtual machines, actually each of those virtual machines has its own kernel. So they are more isolated from each other. They have different views, and they also have different ways in which they can influence each other. So containers by themselves, they are kind of cool, but not really useful. So for example, what happens if you start a Docker container and then you kill it? It will simply be gone. And what we would rather expect, we actually have certain kind of primitives where we can say, I want 5 instances of this Docker container running, no matter what's happening to that process, no matter what's happening to my infrastructure. And this is actually where container orchestration comes in. And container orchestration has kind of like different focus areas. So the first one is, as mentioned before, just the container scheduling. So how do I make sure that I have n instances of a certain container up and running? The second part is in kind of like resource management. How can I make sure that a container doesn't land on like an overloaded machine and actually gets access to enough hardware or resources in general? And then the last part, which I see as probably the most challenging, but also the most beneficial attribution container orchestration gives us, is actually service management. Because typically a single container doesn't give us too much. So typically if we look at our applications, microservice architectures, we have a number of different containers which we need to connect. They have to be able to discover each other. So on which host, on which boat is a container running, and how can I connect them together? And the kind of default container orchestration choice nowadays is called Kubernetes, and I assume most of you have heard about that already. Kubernetes actually stands short for like pilot or helmsman of a ship. I think that's a pretty good comparison. I could actually say it's kind of like the helmsman for an entire fleet, so to speak. But if we look at it, it actually helps us to run those containers across like large infrastructure nowadays, several thousands of machines in some Kubernetes clusters. If we look at Kubernetes by itself, it's actually, it has many moving parts, and we don't have to understand all the details. But what's important for this talk is to kind of understand that on the one hand, we have the master nodes hosting the API service, kind of channeling all our requests and scheduling the different pods. And then we have the worker nodes running the actual containers. And this is where we're going to see a bit more in here. In Kubernetes terms, if you haven't encountered that, a pod is either one running container or a collection of running containers sharing certain namespaces. And so basically here in the worker nodes, we have multiple pods running. We have the kubelet as kind of the controller. And then down here, and this is what we'll mostly be concerned about, we have our container engine, Docker, CRI-O, or other things actually starting the container and managing the different containers. So containers, for me, the kind of, as I mentioned, like one of the first most important lessons probably there isn't this core concept of a container. So there isn't like a fixed abstract concept, but it's more a specification. And I believe the biggest benefit containers allow us to do is standardization. I know I can run the same container on different platforms with the same commands, and I don't really have to worry about where I'm actually executing that. That's first of all because we have standards, which we'll see in a second, like OCI, so different tools can actually execute the same container. And secondly, containers allow us to kind of package an application together with all its dependencies. So we don't have to make any assumptions of what's running on the different nodes. These thing which containers don't really provide to us, but still a lot of people assume that, is isolation. So for me, it's kind of important that containers are more about abstraction and kind of standardization than actual isolation between different tasks. So, this actually brings us to the container runtime. So, or more important, the question like, how do we actually end up here? So why do we have so many different container runtimes? Why are there so many different projects? In the early days, it used to be super simple. I mean, there were C groups, there were companies like Google doing a lot of that stuff. So for example, I worked on Apache Mesos. So we also kind of built our own containers on the fly. But for most of the world, it was just Docker being an all-in-one solution. So Docker, if we talk about Docker, we can actually mean totally different things. So first of all, it's a container image format, a Docker image. Secondly, it's a method for building a Docker image. So if you ever done Docker build on a Docker file, you built your own Docker image. It's a way to manage container images. So for example, with the Docker command, you can see all the images you have on your local machine. You can remove images and so on. Secondly, Docker is also a tool to manage running container instances. So if I have a container image and I want to run that, then I can use like Docker PS, also Docker RM. I can also use Docker to share images, so by Docker push pull to certain registries, which is centrally hosted. And obviously, it's also just a way to run containers to Docker run. And I think this already shows, this is actually covering a lot of different tasks which we might want to separate from each other. Second thing, if we actually look at the kind of Docker internals, there's typically like this Docker daemon, and this Docker daemon is executing all those commands and makes sure something is happening. So for example, Docker push, it just first gets sent to the Docker daemon, and then the Docker daemon will make sure that gets executed. So, and this is actually also how Kubernetes started out in the early days. So there weren't multiple container runtimes. It was pretty much all built around Docker as the container runtime. So there were a lot of commands wrapping using Docker pull, using Docker push, and it was pretty hard-coded in the code bases. And I would actually go as far and say it took Kubernetes about half a year of work at least to actually get rid of all the Docker dependencies once they decided so. So I would say it actually held up the project for quite a bit. But on the other hand, you can also say it accelerated it in the beginning because there was just all this Docker infrastructure available. Then actually came out other projects. So for example, the first one, which by now is unfortunately deprecated, was Rocket. And the idea when for Rocket was that if we look at all of this, what Docker is doing, we don't need all of this inside Kubernetes. In Kubernetes, we mostly care about having something lightweight to run and manage those pods down here. So this full-fledged Docker daemon with all its different capabilities was just too much, and also being a security risk. The more functionality you have, the more different vectors you actually have to attack a certain system. So this was kind of the idea for Rocket to have a lightweight basic unit of execution for running a pod without all the fuss around that and all the other stuff Docker included. Then actually this led to an interface called CRI. A slide on that? I think so. Otherwise, by the way, there are many slides which I've hidden as we don't have that much time, but I'll share the full slide set after this talk. So feel free to also go through the hidden slides and look at them. So a CRI is the container runtime interface, and that actually allowed for the first time to plug in different container engines down there. So all of a sudden, Docker was just one of the potential engines to be running Kubernetes, but there were actually others. And so this actually led to a large number of options how we could run containers in Kubernetes. So just recall the kubelet is kind of that node worker controller starting all the different containers. And as we can already see, there was a number of options. So there was a Docker shim still running kind of the Docker daemon. There was a CRI containerd running containerd, kind of the open source version then of Docker. There was CRIO, so the OCI-based implementation of the container runtime interface with RC. We could still use containerd with Kata and Firecracker, and so on and so on. So the point of the slide is also not really to go into all those details, but it's just to kind of show, oh, we actually end up with a large number of different options, what we can use as different container runtimes inside Kubernetes. And yes, mentioned. So also if we look at the Kubernetes documentation, we can see there are a number of different supported runtimes. So probably the most prevalent ones, it's still Docker, there's CRIO and containerd, and also a number of other runtimes. So especially underneath containerd, we can also use a number of different other projects. And don't worry if this still sounds like all too much for you right now. This is exactly why we dive into details in this webinar. If we talk about container runtimes, there are actually different levels or different granularities of which we can talk about container runtimes. So on the one hand, there are runc, which is a pretty low-level thing because it's just really focused on executing containers. And on the other, they're like full-fledged daemons, like containerd, taking care of more tasks of the entire container lifecycle. And so the first thing for all of this ecosystem to work was the OCI standard, or the OCI initiative, which allowed us to actually have a certain standard for containers. So with OCI, if we have an OCI compliant container spec, and we have an OCI compliant runtime, which for example Rocket and Docker were, we can just with that same image do something like Docker run example blah blah image, and the same with Rocket run example com image. And this was already really helpful, and it basically consisted of two parts. First of all, the image spec, saying like basically how here example.com org app v1 looks like and how it can be unpacked. And then on the other side, how the runtime spec actually should deal with that, and the runtime spec needs to be able to start that process. So those are the two parts of OCI. And then in Kubernetes, and as mentioned, that was one of the big rewrites, probably taking at least half a year. We arrived at CRIO, so Container Runtime Interface, OCI. And this is the OCI-based implementation of CRI, so kind of like the default reference implementation as well. And if we look at that, how that looks like, then if we start a container in Kubernetes, we have our API server. That the API server is talking to the kubelet saying, hey, please start something. And then basically the CRIO will make sure talking to that container runtime down here, and that will then actually start that pod. Next slide. Then we have runc. As mentioned, that's kind of the low-level tool, the low-level runtime, and it's actually the open source version of the original Docker runtime. So it's actually just that part which runs a container. And with that, it basically looks like, hey, we have here a host kernel, we have multiple containers on top, and it really just does keep a container spawn it, and then run a container. Then we actually have container D. So container D is then the daemon managing the entire lifecycle. So to start a Docker image, we have to do a lot more than just run it. So we first have to get the image from somewhere. We have to make sure that we prepare everything like storage. We have to make sure we actually call down there to call runc. We have to create all network C groups, connect to network, and so on and so on. And so this is basically what container D does for us. And as we can see, it can then rely on runc down here to actually run that image. And I think this is, just briefly going back here, this makes it a bit hard if different people talk about different container runtimes, that actually container D and runc might be both named container runtimes, but they actually work on different levels and one might use the other. So I think we already talked about most of that. So if you just recall this Docker daemon, so this is the Docker daemon is this always running agent daemon, which I can talk to, which the CLI can talk to. Any Docker command I'll submit will go through there, and then it will actually trigger all the other things. And so there's actually all other Daemonless container engines where I don't actually need always this running container, and especially in the beginning, I don't know how many of you remember that Docker daemon always used to be like a really pain. So for example, initially when upgrading Docker from one version to the other, so I had to take down the Docker daemon, that would kill like all my running containers, and so on and so on. So this is why actually a large number of people today prefer daemonless container engines. And so probably the most popular is Podman. And you can do just an alias docker equals Podman, and your same commands are just going to run the same way. I mean, there are some exceptions if you're doing like really deep down network stuff, but for most use cases, you can actually just alias Docker with Podman. And that will also allow you to just do Docker, or in that case, Podman run a certain image, and it won't rely on that ever running a daemon. It will actually start small daemons monitoring each of your running containers, but it won't actually have that big central daemon as Docker does. So much to the different container runtimes, and I'll summarize it a bit in the end, but I don't believe it's something you have to be too concerned about. It's interesting because Containerd and others are offering you more choices for different runtimes, but it's typically something you don't really notice, especially if you run on a managed Kubernetes solution. Let's talk a little bit about security here. So there are a number of different vulnerabilities, and I always find it really interesting to look through those when it comes to containers or C groups. So for example, here is one which actually, by incorrectly handling copy on write, this actually allowed us to kind of like get out of our container and take over potentially other Docker containers or even the host kernel. So if we run in a shared environment, so especially, for example, consider us with Oasis, this is actually something frightening, and we should be a bit worried about that. And this actually led a large number of people, especially the big cloud providers offering managed Kubernetes solutions like AWS, Azure, or Google, to kind of revisit that idea: is container actually the right abstraction? I actually know a number of like smaller container hosters or container providers who already start a virtual machine for each container they start. And this is also where people kind of try to find that middle ground. And maybe just why do we actually have to choose? Why don't we want to start a virtual machine for anything? A virtual machine actually comes with a lot of overhead in terms of resources, in terms of startup time. But on the other hand, just provides that real isolation guarantee, as I can kind of, as each container or each virtual machine has its own host kernel, and so it really reduces the attack interface. And this kind of leads over to the second part of this talk, where we talk about secure containers. And the first project was originally started, I think it's named Light Containers by IBM, Kata Containers. And those are actually lightweight virtual machines. So it started out by leveraging the KVM hypervisor, which is a very default battle-tested hypervisor for virtual machines. And then it actually used a QEMU to start virtual machines to kind of like wrap each container into its own QEMU virtual machine. They use some performance tricks like kernel same page merging that we actually don't have to duplicate all the resources or can kind of benefit from some side effects. But there's still the overhead from like disk, memory, CPU, which we kind of see with virtual machines. Still, a lot of people like that, and Kata containers actually made it really easy because they were integrated via containerd into that entire container, and especially Kubernetes ecosystem. So there are actually multiple ways to run them, but it made it very easy to kind of work with that, and also kind of, besides the performance implications, it was very easy switch. I think I'm going to shift over that, but it basically, this slide would go into the details how containerd can be used different ways to start the different Kata containers. The next open project which came up was Firecracker. So one challenge with Kata containers is that QEMU is still a pretty big virtual machine. So this was built to run like any kind of virtual machine. And especially AWS, when they developed Firecracker, they wanted something for like the small, especially function as a service. So they particularly built that for a function as a service, where you don't need all the capabilities a normal virtual machine might have. You don't need a full-blown network interface supporting everything. You don't need all the I/O stuff. You don't need a full-blown virtual machine, but actually a small subset is, first of all, more secure, because again, I have less attack surface, and secondly, also way more efficient. And so this was the idea for Firecracker. And so Firecracker, you can imagine as an alternative to QEMU in this picture. And so we can still use KVM underneath, but instead of using QEMU virtual machines here, or virtual machine monitors, we can use Firecracker instead. It's only emulating a smaller number of devices like virtio.net, virtio.block, SOC, serial console, and a minimal keyboard controller. I think that's only needed for a startup mostly. And this leads to like much smaller things. So we end up with like a millisecond startup time, and just with like a 5 megabyte footprint. And this already makes it like way more usable. Just keep in mind, it's not like a full-blown virtual machine, but it actually allows us to run for most use cases for most containers. Firecracker itself, it might be a bit challenging to compile, but luckily there are a number of other projects. So for example, Weaveworks came out with weavignite, which is that virtual machine manager, which actually makes it super easy to get Firecracker virtual VM started, because I can just give it a Docker image, and Weave will actually create that virtual Firecracker virtual machine for me. So if you want, Weave is basically an easy way to work with Firecracker, unless you're building infrastructure like AWS for your function as a service, where you probably want to use Firecracker directly. Then the Kata people, as mentioned, they initially were using a QEMU but they actually also picked up on that idea that this totally makes sense. And so we kind of can end up with this stack right now. So you have your kubelet, then you have CRIO or containerd calling the Kata runtime, and then the Kata runtime will create a Firecracker virtual machine or a Chemo virtual machine based on your configuration. And I think this already kind of shows the different layers in those stacks quite nicely. So here we have kind of the container management system, and then for the different runtimes, we here either have the runc, which is kind of the original container version, just creating C groups and namespaces. And then on the other, we can leverage Kata, the Kata runtime, then creating a Firecracker or a Chemo virtual machine. And I hope you start to see like at which different layers those different projects are coming in. And I think this is those different layers. This is what makes it so hard for us to grasp or so complex because they all just serve different capabilities. And initially, when Docker came out, it was just all this one Docker project. Nabla containers. So Nabla containers is another interesting project. I'm not sure how many of you have heard about Unikernels. So the idea is basically we build kind of our own, we compile our own operating system with only the things needed for our container. So we take our container, we know what it needs, and so we actually compile a specific version. So we kind of compile the kernel together with the application into a unikernel. And so again, the main initiative is to really reduce the attack surface because we don't have anything in addition. And then the kind of interface to the host kernel when we run with Nabla containers can be limited to few native syscalls in between here. And if you care about how that's implemented, this is actually like filtered through seccomp. So we can just make sure that there are no other calls here in between. And then here, our container is actually our compiled unikernel, which was compiled against this library OS. So yeah, with that, our application basically gets built, or I would call it compiled against libOS into this bunch up here, which combination of libOS. So just keep in mind, there might actually be a number of syscalls in here, but libOS is going to make sure that this all gets handled internally, and then seccomp is ensuring that I can only use those 7 syscalls mentioned on the earlier slide as kind of the interface to the host kernel. And again, this can run similarly on like runNC, which is the equivalent like run Nabla containers to runc, and basically gives you quite secure medium overhead containers. From my experience, just the build process here is a bit annoying, and it won't work with all applications depending on the syscalls you're having. But for most containers I work with, this actually works rather fine. Then Google also has its own project. So this is called gVisor. And they actually did something where I feel that only Google can do that. So they actually re-implemented a large chunk of the kernel in Golang. And so how that then works out, we have our application making system calls. And those system calls are basically captured by gVisor. And gVisor will handle most of them internally. And then there's, again, similar as actually here, a limited interface of syscalls, which are being passed through to the host kernel. So it's not as here where each container, so maybe just to compare the differences. So with Firecracker, actually each of those things has its own full-blown virtual machine. If we use Chemo, like a really big virtual machine. If we use Firecracker, a bit smaller virtual machine. If we use Nabla, we kind of compile our own application. And with gVisor, it's actually our application. We have a kernel in user space against which the syscalls are being made. And then gVisor kind of gives us less isolation compared to a full-blown virtual machine. But on the other hand, it also is a bit more lightweight. We have still a performance impact, especially for like network and storage. So there are also kind of flags by which you can say, hey, please pass that through directly, as we, for example, also have to do with GPUs, where then the application can directly talk to the host kernel. And so just in like our pictures we've seen before, kind of gVisor is this kernel and user space lying in between the container and our host kernel down here. runv is another hypervisor-based OCI runtime. So in short, it allows you to also kind of run your containers, OCI-based containers as virtual machines. So as mentioned, there are those kind of three different extremes. On the one hand, if we use runc as a native container, so just using C groups and namespaces, it's fast, low overhead, and I think this actually led to the success of containers. But on the other hand, we actually have very little isolation in between containers. Kind of that middle ground are the user space kernels, where we already really reduce the attack surface. So if we look at gVisor, which is one example of those user space kernels, we go down to about 80 system calls, which can be passed down to the host kernel. So already much less compared to like 300 or even more on an application level. But on the other hand, this requires that special build. If we talk about virtual machines, so Firecracker or Kata containers, this is probably the safest because we have the highest isolation. But on the other hand, we actually have to pay with performance penalties and resource overhead. So what does it mean for us? So if we are running stuff, so as mentioned, for container runtimes, this is standard stuff. So I'm looking at like, what does my cloud provider support? What's most convenient there? Because in the end, in most cases, it doesn't make that much difference for myself. Still, for the secure container side, it really depends also what my cloud provider or my Kubernetes is offering. I typically feel if I run stuff where I'm kind of sure this is under my own control, I'm really controlling all the images myself, native containers are actually not that bad, especially if I have like some checks in the CI pipeline, checking for vulnerabilities. If I need more isolation, so for example, running in a multi-tenant setup, I would actually go somewhere here where gVisor or user space kernels, they kind of give me that middle ground, already reducing the attack surface. And then if I really, really need to be safe and I want that each of those containers / virtual machines has its own kernel, then I would actually switch into that field of Kata containers or Firecracker with Ignite. So I think this really depends on what am I running in a multi-tenant environment? Am I running user-defined code? So for example, if I'm running function as a service where users can actually provide that code which should be run, I'm obviously at more risk. And then secondly, what is the kind of risk impact if something goes wrong? Am I exposing user data, or am I just breaking the platform running there? So I think those are kind of like those three different approaches we can look at. I've seen few people going for Nabla so far. I think it's kind of interesting, but it's still kind of complex to build that build pipeline for Unikernel-based virtual machines. If we're talking about different acronyms in that space, there's also CNI, the Container Network Interface, CSI, Container Storage Interface, CRDs, custom resource definitions. So I think the Kubernetes space still has a large number of different acronyms on hold for us. So I would actually want to open that up a bit for questions because I would be curious, what are you running? What are your concerns about container runtimes? And do you have any other questions regarding them? So first of all, thanks for listening. I hope you learned a little bit about what different container runtimes mean, or what it means. And we could kind of give a short overview of this field of all those different logos. I said I'll share those slides. There are a lot of comments, there are a lot of hidden slides, but just in terms of time, I also couldn't go into too much detail. So I would just hope that this kind of serves as kind of a roadmap from where you can start your own investigation. And also just feel free to ping me on the community Slack, the Arango DB community Slack, or any other medium if you have any other questions. And also right now, feel free to just post questions in the Slack. Thanks for listening.